Hello, ladies and gentlemen. Joining us today for this webinar titled Composite Engineering and Laser Projection, Improving Production Using a Digital Workflow, brought to you by Composites World and sponsored by Siemens. My name is Jeff Sloan and I'm the editor of Composites World magazine. Today's webinar will focus on the use of data interoperability to help composites fabricators using hand layup processes make sure that what was designed is what is manufactured. This presentation will last about 45 minutes, followed by 15 minutes of question and answer. If you have a question, you can type it at any time during the webinar in the question field of your GoToWebinar control panel. This webinar is being recorded and when complete will be made available to you via email from Composites World. This presentation will also be made available by Siemens via email request. Contact information for our presenters will be provided at the end of the webinar. We have two presenters today. First is Lee Hudson, who works in business development and has been with Siemens PLM software for 10 years. Prior to his current position, he served as a Director of Product and Market Strategy for FiberSim and Technical Services Manager in Asia Pacific, developing indirect technical sales channels. Hudson has earned a Bachelor of Science in Mechanical Engineering from the University of Wisconsin in Milwaukee and a Bachelor of Science in Accountancy at Bentley University in Massachusetts. Our second presenter today is Matthias Stein, Product Manager, Business Unit, Industry Products at LAPs headquarters in Germany. He is responsible for the product management of LAP laser projection systems. Lang joined LAP in 2001 and has an extensive background in laser systems. Lang is a certified electrical engineer and started his career as an electronics installer, specialization for systems engineering. Lee, it's all yours.
Thank you, Jeff. Just a quick rundown of what we'll actually talk about today. I think we'll give an overview of both Siemens and LAP. We're going to talk a little bit about the challenges that are occurring between the use and sort of managing the digital workflow and between the use of an engineering definition and how that's making it downstream to manufacturing and specifically laser projection systems. We'll talk a little bit about the solution or give a quick overview of the solution. And then we'll talk about FiberSim as a part of that process and LAP as a part of that process. And then we'll wrap up with providing our contact info again if there are any additional questions. But then we'll have a Q&A session at the end of this. So at this point, a lot of people know what FiberSim is. It was actually designed and developed by a company that was acquired by Siemens PLM software about 5 years ago. Our primary focus for what now is become a specialized engineering software business segment of Siemens PLM software. Our primary focus is automotive and aerospace industries. And the solutions that we actually develop are specialized domains such as FiberSim for development of composite components in those industries. Our solutions are very industry focused, meaning that we've built in the best practices from those industries for the solutions that we provide. Those solutions are end-to-end solutions, being very synergistic with the rest of Siemens PLM software, and we maintain a multi-CAD and open architecture with all of our solutions, so they don't just work with, for example, a specific or one particular CAD solution or one particular analysis or manufacturing solution, but we try and assist our customers in achieving an end-to-end process with that open architecture, no matter what their engineering tools are. We have about 300 customers globally and continuing to grow in both those automotive and aerospace industries.
Okay, thank you, Lee. It's Matthias now. In 1984, LAP, being pioneers in laser technology, started to develop point and line laser units for industrial measuring systems. Today, LAP is in ISO certified company providing quality laser solutions to the global markets. We are active in 3 business areas, offering industrial laser projection, laser measurement, and healthcare solutions. LAP's headquarters is located near Hamburg in Germany, and the LAP staff takes care of the company's worldwide customers through subsidiaries in the USA, Singapore, and China, as well as a network of more than 70 distributors worldwide. The focus of our business is to improve process performance and to assure quality within manufacturing lines.
Thank you, Matthias. So to talk a little bit about the challenges that are occurring with manual composite layup, and there is a significant amount of manual composite layup that still occurs out there, is really trying to capture and exchange a complete engineering part definition or composite part definition between design and manufacturing. What we've seen in the past and sort of people that are sort of moving in the best practices direction is that they'll often have data that describes what the ply is. For example, in the CAD system, they may have curve boundaries that get exchanged with a laser projection system such as LAPs, but not the complete definition. And so when I talk about the complete definition, I'm really talking about, geez, what's the fiber orientation? Where are the areas of importance during the layup? Those things need to be captured and also passed downstream in order to achieve a higher level of quality and consistency in manufacturing. We also have seen that updating manufacturing data becomes a challenge, especially when the design data and the manufacturing data are being managed separately, and being able to make sure that the version of the data that's being used on the manufacturing floor is actually the proper version of the data. So we've experienced a lot of challenges just in sort of the communication process downstream from design to manufacturing.
Okay. Despite automation possibilities, the often complex forms with high demands on quality require an enormous amount of manual labor. The manufacturing process involves manually laying down individual layers of plies. From our standpoint, there are essential 3 issues when it comes to layup on the shop floor, and all are about improving quality and increasing efficiency. When positioning large materials during production with composites, many companies use manual measurement methods for alignment. This procedure is very time and cost consuming and lacks flexibility, especially when changes have to be made. To respond to the demand on efficient and flexible manufacturing process, digital production tools and a consistent digital workflow are crucial. Preconscious is that the laser projection data is available straight away from efficient tools like FiberSim, and that they are transferred precisely, fast and true to scale onto the workpiece. Another critical point is to make sure that the ply the person is laying down is the appropriate ply and that is laid up on the correct position and order. The second important issue is to validating fiber orientation, which is essential for product quality. So, give it over to Lee.
Thank you, Matthias. So one of the solutions, and again, this goes back to the open architecture of FiberSim, one of the solutions is a combination of design for manufacturing and being able to reuse that data downstream. So one of the solutions that we'd like to propose today is actually a solution between FiberSim and Composite Pro. It provides a much more precise and faster way to actually achieve manufacturing. And part of the way it actually does that is through the design for manufacturing process in FiberSim being addressed up front, and then being able to consume or pass that data downstream and consume it in manufacturing. It removes the, shall we say, the manual templating that used to occur in scribing on the mold itself, and also with physical alignment of the tool and physical alignment of the boundaries, is part of what the data that comes from the CAD system and then gets passed to LAP's solution allows you to do that in much quicker and with much more precision than you were able to do with templating and scribing. Even complex contours themselves are projected much more precisely. Simpler, it's much easier to transfer from FiberSim composite definition, directly onto your workpiece through this interoperability between FiberSim and Composite Pro. And then being able to make design changes easily and ensure that they're communicated downstream, and again that manufacturing is using the correct version of the laser projection data versus trying to go back and actually manually modify laser projection data in order to make the changes that are necessary. They can come straight from FiberSim. Matthias?
Okay. Yeah. As Lee pointed out, using FiberSim and LAP's Composite Pro together solution, layout processes become more precise, faster, simpler, and consistent. LAP's Composite Pro solution has been created especially to address the needs of the composite market. The solution includes everything needed to support hand layout process of composite manufacturing. It consists of high-precision CAD-PRO laser projectors and the ProSoft laser projection software. It utilizes projection at the speed of the light instead of time-consuming manual alignment. The projected laser lines are based on your technical drawings in various CAD file formats. The data can also be exported directly from the Siemens FiberSim software and opened in the LAP laser projection software. If changes are made in FiberSim, they can easily proceed by the LAP software. For projection, you only need to upload a new projection file. You can call up and then proceed projection files on a step-to-step basis. Every work step is saved and documented. That means a consistent digital workflow without media gaps and discontinuity. The great benefits are you can optimize the process sequence and your production quality. In the manufacture of practically all hand layout composite parts, you can work faster, more flexibly, and more precisely than with mechanical templates or other aids for measuring and positioning. Customers report to us a fast, simple, reliable, and cost-effective solution that helps them to speed up their production by 25% or more.
Thank you, Matthias. Yes, thank you. So I'd like to now talk a little bit about what FiberSim is and then talk about how it fits into this process. So FiberSim really is a specialized engineering environment for design and manufacturing of composites. Its environment is actually the same no matter what CAD system that you see on here that is supported by it. And so the experience for the user is actually the same no matter what CAD system that they're actually using. And so we actually will support NX with this specialized environment, but we also support CATIA and we support Creo from PTC. The first step in the process is actually to achieve a actual composite design. And there are, as I said before, industry-specific methods that are sort of tied to approaches for example, large panels for aerospace industry or smaller parts for substructure. We've got solutions that support different industries, even such as wind blade design. And so we've taken the best practices from composite design in those industries and captured them within FiberSim in order to make the process easier. One of those methods actually is called multiply. It allows you to use sort of a hybrid approach between full automation of composite design that is, shall I say, specification driven as opposed to geometry driven, and the manual process, or the flexibility of a manual process where I am creating geometry for everything. These hybrid approaches allow greater efficiency in the design process themselves. And for example, a multiply method themselves would allow somebody to define what we call overlay zones, which are these independent zones that are general ply shapes. The user creates minimal geometry and defines the specification in order to achieve the rest of the composite design and the boundaries for all of the plies. When I say it's an automated process, it actually does achieve an automation that's not achievable with a manual geometry boundary creation approach or a curve boundary creation approach. People would define, for example, material specifications or the material requirements for each one of the regions of the part and the general ply shapes, and then they define specifications such as offsets or drop-offs, offsets for drop-offs from thicker to thinner regions, or the cross-sectional profiles of those. And so what you see on the screen here is actually not geometry that was created by a user in the CAD system, but created by a user in FiberSim by defining specifications, which ultimately makes the, we've been talking a little bit about the change process, but it makes that change process much, much easier. And we've experienced from customers that are using hybrid approaches to design upwards of 80% of efficiency in terms of the design process. I mentioned earlier about, excuse me, I mentioned earlier about design for manufacturing. To me, this is one of the pieces that our customers are able to achieve with this combination of FiberSim and LAP's solution, by being able to do things like run these manufacturing simulations that understand what the deformation of the material is going to be, whether it's actually going to cover the part even from a material width standpoint, things like steering and even fiber deviation, because you're trying to achieve some specific structural performance for a particular part. And being able to identify those challenges early allows you to add additional data to the design that's useful in manufacturing. And I'm going to give some simple examples, right? If I'm going through and I'm trying to lay up a particular ply, for example, on this tool, and I find out that it can't cover the area that I expected it to, I'm going to have to splice that. If I have a situation where I'm going to end up with deformation, perhaps one of the solutions to that deformation itself is going to be, to splice or to dart that particular ply in order to relieve that deformation. I want to know that before I have to pass it out to a laser projection system that's going to project a boundary that might just be, the original boundary that looks like this, where I've got a complete coverage or a full body ply on a tool that isn't really what's going to end up happening on the manufacturing floor. And so in order to achieve consistency and quality in the manufacturing process, I want to know what changes are going to occur due to the manufacturing process itself up front and be able to communicate those downstream. That manufacturing data becomes significantly important from the standpoint that there are the data should serve really three purposes for the folks that are on the manufacturing floor. And really from a laser projection standpoint, despite the fact that we have a large ecosystem for manufacturing, we're here to talk about laser projection. Well, from a laser projection standpoint, the data that gets consumed on the manufacturing floor should really serve three purposes. It should accurately project the ply boundary for proper alignment on the tool. It should help validate that the correct ply is being placed at the correct time, and it should improve the quality of the layout. Now, the only way to ensure that all three things are happening from a composite standpoint is by taking into account the manufacturing producibility early on and addressing it through design for manufacturing so that you will deliver 4 ply boundaries, ones that have addressed design for manufacturing through splicing, through darting, and even automated manufacturing processes. We have customers that are using things like, fiber placement that end up stopping the machine because there are limitations to the tool, and they use laser projection to ensure that someone's laying toes in the proper area on that particular layer of material that's being put down. Then for validation, the proper order needs to be communicated through the data from engineering to manufacturing. That should include things like ply names, sequence, and the data should be projected at the proper location and at the correct height in the stack up. Parallax error is important. We've seen it time and time again. Things like improving the quality, though. Projection data, should generate things like start points, direction curves, and even things like markers, which become crucial in terms of making sure that you're achieving the structural performance and consistency during the layup process. So again, trying to reuse is actually the most important point of being able to go directly from the design data to the manufacturing floor. That digital flow, digital workflow is consistent throughout the process. And if something happens from a design standpoint, there's a design change that comes through, it doesn't take days to actually get that back out the door to the manufacturing floor. It's simple enough with an automated design process such as FiberSim presents to be able to make those changes, regenerate the data, and get it back out to the manufacturing floor. And then in addition to that, we also allow the user to verify the laser data before they actually send it out to the manufacturing floor. Or if somebody on the manufacturing floor has a version of FiberSim, they can validate that data through imports back into FiberSim and view it within the context of the CAD system itself and of the CAD model itself. So not only do we generate the data, but we allow somebody to go through and take a look at that data and make sure that it is accurate. And I mentioned it earlier, and I have seen it too many times, unfortunately, where what the manufacturing floor ends up using is a version of the data that doesn't match the revision that should be out on the manufacturing floor. And so one of the things that I want to point out here is that when you're using FiberSim with CATIA or with NX or whatever, you're able to then manage the manufacturing data, and what gets consumed on the manufacturing floor is actually revision managed. And so there's confidence that's built into that they are using the correct data out on the manufacturing floor. And so that digital thread to the shop floor becomes extremely important. LAP, we actually will exchange data directly to LAP CAD-PRO. We are providing data for both tool calibration and for ply projection. And in that slide projection is all of the design for manufacturing data. It includes the important information about fiber orientations and critical areas of the part. It tells the user where they're supposed to actually start the layup process, and sort of what that process is supposed to be in order to go from a flat pattern to that boundary on the mold itself. So that's sort of the I'll say the short version of the role that FiberSim plays in laser projection.
So, thank you, Lee. So I start here. LAP laser projection system, CAD-PRO, consists of one or more CAD-PRO laser projectors, laser targets, the ProSoft software, and one or more remote controls. The LAP laser projector displays precise outlines, templates, patterns, or other shapes on almost all surfaces. The laser projection is thereby based on CAD data provided by the customer. The lasers are mounted over the working area. They can be attached to ceilings and beams in a fixed position or to pivot arms or rails so that they can move. The projection surface may be flat 2D or curved 3D. The LAP projection system secures the correct positioning laser image of the CAD model lines on the surface. The laser image of the CAD model can then be used by customer to join parts, place layers of material, align parts, display work steps, control completeness, or support any other work with the help of the visual laser lines. LAP laser projection systems are deployed worldwide in many industries, in particular in composite manufacturing of aircrafts and wind rotor blades. I will show a small video, I think. Start with calibration. The laser projection is based on your CAD data that has been prepared for laser projection. For a precise one-to-one projection, calibration is necessary. The projection system requires the target positions, calibrating data, and the projection data and the tool coordinate systems. The basic calibration is required just once immediately after installation. Afterwards, the system checks the calibration automatically within seconds. For calibration, the system scans the targets located at survived points. From this, the system calculates the position of the projector relative to the projection surface. This enables each projector to correctly display the projection. To cover large areas, up to 16 projectors can be combined in a system. It is possible to project images in different colors for different or important work steps in the process. Positioning the projected lines and the predefined projected sequences help the worker to place supplies in the correct order at the correct place. Once the item has been placed, the following ply can be positioned precisely with the projected outline. In this way, the worker is visually guided step by step through the complete layout process. So far theory, but what does it look like in practice with a real projection file? In the following section I will demonstrate how Siemens FiberSim solution interacts with the LAP laser projection system. I will show how the projection file generated by the FiberSim laser projection module may be easily handled by the user-friendly LAP laser projection software ProSoft. LAP ProSoft guides you from the import of CAD data to the projection itself and back to a CAD file if required. I will also present how the actual laser projection is created. I captured the ProSoft and show how to open a calibration file, open an automatic or calibration. After that, automatically start the projection. And the system requires an order number to create the log file later on for the administrator. So now the user can start with the first projection here. And we see now on the tool the projection in red lines. Switch to the next projection you can do by the desktop. Here I switch over to project also to the text. You can switch or toggle in between text and graphics. Here we can see different languages from the software and the different views you can select. So I switch to the contours, and the system asks the user now to check or recheck the layout of position number 3, and all is logged in the log file here. So the user has to switch step by step through the projection files, and we see here different projection in different colors, in green and red, and also yellow is possible with our CAD-PRO projectors. And now always is the FiberSim orientation projected, the layout and the text. I show what happened if the user reopened the file, and then we see that the log files start at the last step. Means the worker can stop the work and go on the next day with the same step, and the system logs all the old steps. On the left side, the green positions are late, the red is in process, and yellow is to do. So now the last contour is reached, and the system will be closed and will be then ready for the next open file. As I have demonstrated, the projection file generated by the FiberSim laser projection module can be easily handled by the LAPs software. Thanks to the open architecture and data interoperability with FiberSim, you may immediately start the task in the LAPs software. No additional software for importing CAD data is needed. Files can be opened in the order of position. If changes are made in FiberSim, they can easily be projected. It will be due to the upload the updated file. The result is an integrated digital workflow from composite design to manufacturing. As a conclusion, you can say, project the ply boundary for the proper alignment on the tool, and validate that the correct ply is being placed at the correct time, and improves the quality of the layup. This means optimized layup being much more accurate, more flexible, and faster. I have reached the end of my demonstration and would like to thank you for your attention. At the end of the webinar, you will have the chance to address any question related to LAP solution to me. So give over to Lee.
I think we're going to pass it now to Jeff.
Okay, great. Thank you, Matthias, and thank you, Lee. Appreciate the presentation. So attendees, we do have time now for some question and answer. If you do have a question, go ahead and type it into the question field of your GoToWebinar control panel. And we do have some questions already, so Lee and Matthias, let's go ahead and start moving through these. The first question is this: how does FiberSim support automated fiber placement?
I think that's a great question. We actually support, again, a large ecosystem of fiber placement and path planning solutions. Most of those are from the OEMs themselves. What we do is actually the same thing as sort of we're talking about here, which is, be able to design for the manufacturing process, and then be able to pass that engineering definition and design for manufacturing definition downstream to those path planning solutions. And so it's very similar to what we're talking about here.
Okay, great. Next question is this: how do you control fabric movement once it has been laid up in the tool or the mold?
I think it's a question for my system, for the ProSoft system. To control something, a movement, you can recalibrate the system on every time, or you can select the target check function in our software, and that will control if the target's in position after switching layup, or you can select it after a time, after 8 hours, or every 10 minutes. You can use it like you want there.
Okay, great. Next question is this: how do we achieve the part thickness required by engineering when we fabricate a composite part? Is there some kind of acceptable tolerance between what is being manufactured and what the engineering requirement is?
That seems like a very general question that I think I prefer taking offline. But in terms of what we do from a design to laser standpoint, again, as I mentioned before, from ensuring that what's being laid up is being laid up accurately, we actually take into account the ply thickness as we generate the laser projection data. In terms of tolerances, that's very dependent upon the design itself.
Okay, next question, also AFP related. Please discuss how laser projection integrates with an AFP machine and the interfaces between the Siemens LAP and the AFP software.
I don't know what mean AFP.
Automated fiber placement.
Okay.
I'll be glad to take that one, Matthias.
Okay.
So, as I was talking a little bit about earlier, one of the experiences that we've had is the fact that for fiber placement, for example, minimum coarse corners, things like that, are not always achievable with particular machines, and there are a couple of solutions that can occur. There can be a design for manufacturing solution, which is something that FiberSim supports, or we have customers that will stop the machine and actually manually lay up things like minimum coarse corners, and so they use laser projection in the middle of that process. They'll use laser projection to project the area that someone is supposed to go lay those toes up to achieve the boundary that can't be achieved by a particular machine. And that's really where the LAP solution comes in, is, geez, we've got an area of this particular layer, that area can be defined, and then based on that minimum coarse distance, it can be generated as its own separate manufacturing data set and sent to LAP for projection, so somebody knows where to lay that up and accurately lays that up.
Okay, great. Next question is this: how large of a tool, depth of tool, can a single projection head support? Can you gang heads together for more coverage in the Z direction?
I think it's a question for the CAD-PRO system. So we have an output area or a capturing area from plus minus 80 degrees, and X and Y. So depending on the Z direction, you get an defined capturing area from this angle area. So if you need more details in that, I can send you some more information or something.
Okay, great. Next question. How is the link between flattened patterns and laser projection being ensured?
I guess that's a question for me. So as part of the flat pattern being generated, again, one of the things that FiberSim does is allows you to assess the manufacturing producibility based on three things, right? Based on the part shape itself, the material and material form that you're using, and the manufacturing process that you expect to use, whether that's a manual layup process or something different. But even from a manufacturing standpoint, a manual layup process can be done differently. One of the things that we do with FiberSim is allow somebody to define that manufacturing layup process, and then we can communicate that through things like markers and things like that allow somebody to understand what the manufacturing process is supposed to be with the laser projection system. So we use the producibility in the manufacturing producibility in defining that manufacturing process to then simulate what that flat pattern is going to be and generate the flat pattern. That's what ends up being cut. And then we match that with the laser projection data along with the start point, the manufacturing or information about the manufacturing process, and an understanding of where fibers and fiber direction are important. And that becomes part of the laser projection data. So you're sort of matching what you're generating from the producibility to get a flat pattern with what you're trying to achieve on the manufacturing floor. And again, that's sort of what I was talking about earlier, where quality and consistency it really comes from a combination of using the engineering definition and doing design for manufacturing and using that design for manufacturing data as part of the process that LAP or the data that LAP consumes and the process that they follow and project.
Okay, good. Let's see, next question is this one. This is for LAP. Is it possible to project different colors with an LAP CAD-PRO laser projector?
Yes, sure. I don't see the question. Excuse me? So it's possible to show different colors. You can show red, green, and yellow color from one projector. So you can easily select the color with the FiberSim system as you define the color in the CAD data.
Okay, next question. What is the operation lifetime of the laser diodes?
So the laser diode have 30,000 hours lifetime.
Okay, and next question. How does the LAP solution support layup tasks for large objects, for example, rotor blades?
LAP offers real multitasking for teams working with different tools using shared resources. This is important for large objects like rotor blades. Unique LAP Opto Group, a client-server concept, enables several teams or groups to work at different locations on a large object.
Okay, this next question you may have answered already, Matthias, but I'll ask it. What is the maximum service durability for LAP laser projection, LAP laser projection?
Please get again the service?
Maximum service durability. I assume they're asking how long the laser lasts, and you mentioned earlier in regard to the diodes.
Yes, the lifetime of the diodes is 30,000 hours, and the selecting service is a yearly turnus.
Okay, next question is this. What is the precision of the laser scanner, knowing that the tolerance, especially in aerospace, is very tight?
The CAD-PRO tolerance or the CAD-PRO accuracy is 0.1 millimeter from meter to distance to projector. Plus minus.
Okay.
Plus minus 0.1 millimeter per meter.
All right, next question. On a complex shape, can the laser be used to project the sequence of the area of complexity to be worked by the layup technician, assuming that the start point was observed?
Can you repeat that, Jeff?
On a complex shape, can the laser be used to project the sequence of the area of complexity to be worked by the layup technician, assuming the start point was observed?
Yes, sure. It's possible. It's easy possible by the ProSoft. You can show the defined projection angle, 60 degrees or 80 degrees, whatever you want.
Okay. Well, Lee and Matthias, it looks like we've come to the end of our questions. If there is any more interaction to be done, Matthias and Lee can handle that offline for anyone who still has outstanding questions. But we've come to the end of our webinar, and I want to thank you and Lee and Matthias again for this interesting presentation. We appreciate it.
Well, thank you for having us.
I thank all to listening to us.
Yep, and thanks again to our attendees for taking the time to join us today. We appreciate you being here, and we hope to see you again soon at another Composites World webinar. Have a good day.